Okay, so alongside the two videos that I've already made looking at how to change between different forms of lines, I have 3 further exercises that you've requested that I go through, and hopefully these will provide you with enough of an explanation so that everything seems clear. So the first one that was requested was 14.44, and I've chosen here to go through part F. And in this part we're given 2 lines, G and H, and they're given as their vector equation. And you should of course remember, as I mentioned in the last video, that the capital X should be interpreted as the vector xy, which is the coordinates of points on the line. So all points on the line satisfy these equations, and these equations give rise to all points on the line, just changing the values of t and u. So the first thing with any kind of geometric exercise that I always recommend you do is draw a sketch. And the question asks us to figure out how G and H are located relevant to one another, or respective to one another. So I sketched the line G by first of all taking the point on the line, 5, 4. So I went along to 5 on the x-axis and 4 on the y-axis and plotted a point here. And then I took the direction vector 1 step in this direction. So I went 2 along and 1 down to give me the point 7, 3. And 1 time in this direction, so I took t as -1 in this case, and I went 2 along in the negative x direction and 1 up, and I got 3, 6. No, 3, 5, sorry. And then I join those together with a line, and that line shows me the rest of the points on the line, but of course it's only a very rough sketch. Then I did exactly the same for H, although H was trickier because the numbers were so big, so I got -6, 7, my first point was there, and then when I went along 6 in the positive x direction because of the direction vector, and up 5 in the y direction to get a second point here, and I join those two together. And from my sketch, it's obvious that our 2 lines cross at one point. How could I have checked this without doing the sketch? Well, I know that there are only 3 different options for lines in 2-dimensional space. Our first option is that the lines cross at one point, which it seems that we have here. The second option is that the lines are parallel. And the third option is that the lines are identical. So if you want to distinguish between these 3 things by calculation, your area of interest is really the direction vectors of the 2 lines that you have. In this case, you have that the direction vectors of the 2 lines are not parallel, whereas in these 2 cases, if the lines are parallel or they are the same line, then the direction vectors are parallel. And if direction vectors are parallel, it's basically like saying they are the same direction vector. If I have a direction vector that goes 2, -1, and a direction vector that goes 4, -2, and ends up here, they're parallel. One's just longer than the other. But in the cases of lines like these, it's taking the line in the same direction, and so it's as though it is the same direction vector. And so you should remember that if two vectors are parallel, so if 2 vectors A and B are parallel, then there exists a scalar r. I hope you're almost chanting this sentence along with me in the real numbers, such that A is equal to R times B. And so we need to have a look and see if there's a number by which we can multiply one of these vectors to give us the other one. So let's take this direction vector first on line G, 2, -1. So we have 2, -1. And we have the direction vector for line H, 6, 5. And we need to see if there's a scalar such that we multiply one of the vectors by the scalar to get the other vector. So if we compare the top lines, so let's multiply this one then by the r because that one's the smaller one. And I'll put a question mark there because we're not sure it's equal. If we multiply that left-hand side out, of course timesing by a vector by a scalar means that you times the scalar by both components. If we compare the top line, that says 2r is equal to 6, which means that r would be 3. And the bottom line says minus r is equal to 5, which means that r is equal to -5. So r does not equal r, so no r exists. So 1 must be true. And by 1 here, I mean this one, that the two lines cross at one point. And so it's just a case of checking whether or not the direction vectors are parallel, and then you can see whether they cross at one point, the lines are parallel, or the lines are identical. So we've identified that the two lines cross at one point, and all that's left now is to find that point. And I'll pause the video and rub this out so that I have space to go through that. So now we've determined that our two lines cross at one point, we need to find that point. And in this case, we need to treat the lines as a system of linear equations. So the line G, rather than be written as it is up here, I can multiply the t with each of the components here and add them together within the vector. So I get the line G is actually 5 plus 2t as the top component, or 4 minus t as the bottom component. So that's our x, and that's our y. And this is really just another form of this, but this is the conventional way of writing it, as we have it up here. Similarly, for h, we have x is equal to -6 plus 6u, and 7 plus 5u as the bottom component, and again, that's x, and that's y. Now the thing to remember, at the point where the two lines cross, they have the same x coordinate. So let's say xg is equal to xh, this being xg and this being xh, and yg is equal to yh, where this one is yg and this one is yh. So the two lines are equal at that point. They have the same x coordinate and the same y coordinate. So I can say if xg is equal to xh, number 1, 5 plus 2t is equal to -6 plus 6u. And similarly, the y components are the same. 4 minus t is equal to 7 plus 5u. And now I have a system of linear equations in two variables, two equations, two variables. I just need to solve for t or u, or both to double check, and then substitute back. So what I'm going to do is I'm going to use the substitution method, and I'm going to rearrange number 2 to give me t is equal to -5u minus 3. All I've done is I've changed the sign of the whole thing and then taken off the 4. But you don't have to do this all in one step. You can do it bit by bit, but that's what you should end up with. And then I can substitute minus 5u minus 3 in for this t. So substitute into 1, and I get that 1 becomes 5 plus 2 times minus 5u minus 3 equals minus 6 plus 6u, which gives me 5 minus 6, which is negative 1, plus 6 gives me 5, is equal to 2 times negative 5u is 10u, add this so I get 16u, so I get u is equal to 5 over 16, and then of course I get t is equal to minus 25 over 16 minus 3, which simplified gives me minus 73 over 16, just by putting this over the common denominator of 16. Then my final job is to substitute u back into the equation for h, and my t back into the equation for g, just as a double check, and I should get the same point out. So if I substitute u into h, so instead of writing u here, I write 5/16, I see which coordinates I get out at the end. So I get xy is equal to, on the top, minus 6 plus 5/16 times by 6, which gives me minus 33 over 8, which is 8, 16, 24, minus 4 1/8, which could be about right for my very rough sketch. And for y, I get 7 plus 5 over 16 multiplied by 5, which gives me 137 over 16, which is just over 8. Which also looks about right from my sketch. Then all that's left to do is put t into g and check that I get the same. I'll pause the video now and do that. And whilst I pause the video, I did that for g as well. I put in minus 73 over 16 for t, and I found that I did get minus 33 over 8 and 137 over 16 for my coordinates. So it must work for both, therefore it is the point at which the lines cross. So we're done. Normally the numbers work out a little bit tidier than this, but of course in the real world they don't always turn out quite so neat and tidy, so it's worth getting used to working with these kinds of numbers.